All right, welcome to lecture. We'll get started in just a second. Continuing on, whatever chapter this is now. Chapter 11, I think, is where we're at. All right, so we've been talking about organic chemistry here, and we finished up the alkanes chapter basically. Alkanes, again, all these organic molecules, excuse me, essentially will have some type of part on them, which is referred to as a functional group. And that functional group is basically what determines what type of organic molecule it is. And we talked in the last chapter really about the carbon-carbon single bond, which is an alkane. And again, these are sometimes referred to as saturated hydrocarbons because essentially what that means is they all have carbon-carbon single bonds. And that means that each of the carbons in a alkane, for example, will have the maximum number of hydrogens that it should have. Again, the idea with hydrogen and carbon wants to make four bonds, and everything pretty much is hydrogen bonded to it unless you substitute something else out. Now we started talking about here in this chapter, chapter 11, unsaturated hydrocarbons. And basically unsaturated hydrocarbons means that it at least has one double bond. It may have one triple bond. And as we also talked about already a couple of times, I believe every time you sort of add a bond to a carbon, you essentially will be sacrificing a couple of hydrogens every time you kind of put those bonds on. And what that means is these are unsaturated. They don't have the maximum number of hydrogens that each carbon should have. Again, because they have a double bond, or again, they could have a triple bond as well. And those guys with our double bonds is the functional group for the alkenes. Our carbon-carbon triple bond is the functional group for our alkyne, YNE. And most importantly, as well as we've been talking about, is if you haven't done so already or you're sort of working on it, you do definitely want to make sure that you get a good handle on those alkanes, especially those first 10 alkanes, in terms of the formula, in terms of the names of them, because every other organic molecule that we're going to deal with in this class will essentially always come back to those first 10 alkanes. So it's really important to have a good sort of understanding of those names and the formulas that go with them, because it will come back to them every single time we sort of talk about naming, which we talked about naming alkanes. And when we name alkanes, again, we always look for the longest continuous carbon chain. So as we saw in some examples, the longest continuous carbon chain may not always be the straightest carbon chain. It may go straight for a bit, may go up, may go to the right, and so forth. But you just can't go backwards as you're counting carbons. So you want the longest continuous carbon chain that should match an alkane name, and that will sort of be the base of your name. And then we also have these groups that are attached. These groups basically have one less hydrogen, which allows them basically to attach in without creating too many bonds to carbon. And they also are named based off of those alkanes, most of them. And they're named by dropping the ANE and putting the YL. So a methane with one less hydrogen is a CH3 group. And the CH3 group then becomes a methyl group. Same thing, ethane, if you take off one hydrogen to allow it to connect to the longest continuous carbon chain, the ethane then becomes an ethyl group, YL. So we also want to number the chain. And when we number the chain in terms of alkanes, we always want to number whichever way is going to give the groups attached in an alkane the smallest number. We do put those groups in alphabetical order. So if it's sort of a tie, no matter which way you go, left to right or right to left, in terms of the numbers, then you would want to fall back on alphabetical and give the one in terms of alphabetical the lower number in that particular case. Remember that when we name these things again, it's a number and then a dash to a letter. And if you happen to have two numbers, you separate them by a comma when you do the name. Then we started coming into alkenes and alkynes. Again, they're pretty similar to alkanes in terms of their sort of properties. Alkanes, alkenes, and alkynes, they all are basically carbon-carbon bonds, which is a nonpolar bond. They're carbon-hydrogen bonds, which is also nonpolar. So they're very bad in terms of being working well with water, because again, water is polar. So the idea of like dissolves like doesn't work very well for them. They're good with other nonpolar things, so they're able to interact well, because when they interact with other nonpolar things, they will be interacting with those dispersion forces that we talked about. So they have a way to sort of interact with each other. Now, when we name alkenes and alkynes, which is sort of, I think, where we left off last time, when we go to name these guys, we basically follow the exact same process as we do for alkanes. The goal here is to find the longest continuous carbon chain. Again, may not always be the straightest, may go up, may go down. But important when you're dealing with alkenes and alkynes is that longest continuous carbon chain has to contain either the double bond if it's an alkene, or it has to contain the triple bond if it's an alkyne. So it does have to contain that sort of functional group within the longest continuous carbon chain for it to be. It will still match up to an alkane name. So based on the number of carbons, it'll match up to an alkane. And if it has a double bond, we would drop the ane and put ene at the end of it. So ethane becomes ethene, ene. If it has a triple bond, we would drop the ane and put yne at the end of it. So ethane becomes ethyne, yne at the end. Also different is how we go about numbering alkenes and alkynes. Because the functional group is a double bond or a triple bond, the functional group gets the priority in terms of numbering. So like the two examples that we have up here on the screen that we went through, I think at the end last time, here we have our double bond coming this way. And if we number the carbons, this would be carbon 1, carbon 2, carbon 3, carbon 4. If we went right to left, it would be 1, 2, and 3. So as we saw last time, going left to right will give our double bond the priority in terms of the numbering. And once we lock in going left to right in this particular case, our group will also be locked in to that numbering as well, which is why it ends up at carbon number 3. So once you sort of lock in terms of the numbering, you can't change it up for anything else that's there. You have to stick with that numbering, and all the other groups that are attached would be attached or numbered accordingly. When we look at our guy on the right here, same thing. If we go left to right, our triple bond ends up at carbon 1, 2, 3, and 4. If we go right to left in terms of the numbering, our triple bond ends up at carbon number 2. So again, that carbon number 2 is a lower number. So we would want to number in this case going right to left. And that means because we're locked into numbering right to left, our ethyl group will be at carbon number 4 in that case. So it's very similar to how we name alkanes. The only difference is when there is an option of more than one place where that double bond or that triple bond could be in that molecule, you do have to give the location. And in the name that we got down here, that is, for example, what the 2 means. The 2 means, and the YNE here means that at carbon number 2, there is a triple bond. And just like in the name on the right, on the left here, The 1 here represents that at carbon number 1, ENE is a double bond. We would expect to find a double bond at that location. Any questions on that stuff there that I think we finished on? Again, if you do have questions, feel free to type them in. Even if I've moved on, we'll go back and make sure we get your questions answered and all that good stuff. All right, so let's see what we got next. I'm not sure. Let's see. All right, so let's just see here. I think those are the 2 we actually did name, I think. Let's go back real quick. So these are the guys we just did. So hopefully they'll end up with the same name we did. I'll just scroll through it in case you want to watch it later and you're bored, I suppose. All right. And we're eventually getting there. All right. So why don't you try these here? Why don't you take a few minutes and let's go with the IUPAC name for each of those. Again, when they say IUPAC name, that's sort of the formal, the systematic name, sort of the correct name, if you will. So take a couple of minutes and we'll go through the name of each of these and make sure everybody's on the same page. And again, if you have questions, feel free to ask in this meantime. Okay, so why don't we take a look at these guys and see what we got going on. So again, just like everything, when you go to name them, we're looking for the longest continuous carbon chain. In this case, it's pretty much straight across. So in this case, we do have 4 carbons. Again, the idea here, 4 carbons is based off of butane. Because we see a double bond located, we're going to get rid of the ANE, and that's going to become butene. And again here, since there is more than one option as to where that double bond could be in this molecule, we do need to give the location. And we want to number it in the way that obviously gives the double bond the priority and the smaller number. So it's always smaller number when you're doing it, the numbering. So this is going to be 1, 2, 3, and 4. Obviously, if we go the other way, we're going to end up at carbon number 3 for that double bond. This is going to be carbon number 1. I'll get that right this time. So this should be 1-butene. Now, if we look at the guy below it, it's pretty identical. It also has 1, 2, 3, 4 carbons. So again, it's also going to be based off of butane. Also has our double bond happening there. So it is also going to be butene, ENE. But now the location of that double bond, no matter which way you go, is going to end up at carbon number 2. And that means that this would actually then be 2-butene. Again, the 2 is the location where we find the double bond. And this is a very good example of why we need the number. We need the number to tell people in the first case, the double bond's hanging out over here. And in the second case, obviously the double bond is hanging out over there at carbon number 2. So whenever there again is options as to where you can put either the double bond or the triple bond, that is why we do need to put the number there. All right, let's take a look at the next one. Next one we got 1, 2, 3, and 4. We could also start on the right, 1, 2, and go up 3. That's short. We could start on the left, go 1, 2, 3, and then up, which is 4 as well. So again, when you have multiple ways you could get to the same number, sometimes it's just easier to take the straightest guy. So again, here we have 4 carbons, and that's going to give us the base name of butene with the ENE because we have a double bond. Now, though, we do have something hanging off of it. We have a 1-carbon group, which is based off of methane. And because it's a group, again, it becomes a methyl group. And we do need to number, so we can't go right to left, which would give us 1, 2, 3, 4. We could go, that was left to right. I'll go right to left now. 1, 2, should put some signs up or something. 3 and 4. There we go. Now, when we look at this in terms of the double bond, it is the same number if you go to the right, if you go to the left, no matter which way you go, your double bond's going to be at carbon number 2. So because that is sort of a tie in that case, the next important thing on this molecule in terms of naming would be this group. So it is different depending on which way you go for that group and the number. So when we do look at it, if we go left to right, that group will be at carbon number 3. And if we go right to left, that group would be at carbon number 2. So although it makes no difference for the double bond, it will make a difference for our next important thing, which would be the group. And in that case, we would want to go right to left, which means our double bond is located at carbon number 2. We still need that. And our methyl group would be at carbon number 2 as well, as I try to squeeze it in. So that'll give us something like 2-methyl, 2-butene, the 2-methyl for the location of the methyl group on the carbon, the second 2 for the location of where the double bond is on that carbon. Any questions on that there? And looking at our last one here, again, 1, 2, 3, 4. This seems to be a very popular one here. 4 carbons based off of butane. We got our triple bond. So again, our butane becomes butyne, YNE. Location of our triple bond, 1, 2, 3, 4. 1, 2, 3, 4. Again, there's no other groups attached, so it looks like it is a 2 no matter which way you go. And this would be 2-butyne. Any questions on any of those names there that we came up with? Okay. So we got a couple more, so why don't you give these guys a go? Why don't you give these guys a go while I see what we got going on here? Let me take a look at that real quick. So the question is, why would number 3 not necessarily be pentene? It's because the longest continuous carbon chain, and when you're counting, you cannot go back over. So you have to go one way and then kind of hit a dead end and stop. So if we went one way and hit a dead end, 1, 2, 3, and 4, we can't go backwards though and start counting this way. We went 1, 2, 3, and went up would be 4 as well. If we started up and went down, 1, 2, and went to the right, that would only be 3. So the rule on counting is you got to go until you hit a dead end and stop. You can't backtrack. So that's why the longest continuous carbon chain would only be 4 in that case, and not the 5. Even though it does have 5 carbons, you can't. They're not all sort of continuous because you have to sort of backtrack to get to it. And obviously this one, this line's a little off, and that's actually attached here. I missed that carbon by a little bit. uh, I'm not sure I truly understand your question, but in order for it to kind of get the pentene, you would need something like, say, this steel. If you had something like this would be 1, 2, 3, and then you could go up 4 and 5. And then this would be your longest continuous carbon chain, which would get you to pentene. Again, going the other way, without the extra guy there, you would need another carbon to get to that pentene part. And then this would be the group that would be attached. Yeah, so the real key in terms of counting is sometimes people, I'll just draw the line, people start counting, they go up and decide, well, I'll come back down and go this way. And that's, you can't do. You can't kind of backtrack. So you guys pick a starting point and just go in a continuous way. It could go straight, you could go up, you could go to the right, but at some point you kind of like hit a brick wall, and then you got to count how many carbons you have between those points. Again, you can't kind of hitting a U-turn and go back the other way and keep counting. All right, so let's take a look here and see how we're doing. This guy here looks pretty straight. So we got 1, 2, 3, 4, 5. So this would be 5. And again, this 5 carbons would be based off of pentane. Here we have our triple bond happening. So again, we're going to get rid of that last part, and that will be pentyne, Y-N-E. Now, there's no other groups attached, as this whole thing is the longest continuous carbon chain. So we want a number 1, 2, 3, 4, 5, or we could go 1, 2, 3, 4, and 5. So in this case, going right to left is going to give our triple bond the smallest number, and that number would be 2. So this should be 2 pentyne. Rolling over here, where again, this guy kind of missed the carbon. Happens, I guess. If we count here, we got 1, 2, 3, 4, 5 if we went straight. We got 1, 2, 3, 4 if we went up. We also have 1, 2, 3, 4 if we went the other way. So it does look in this case that the straight one here, and again, it may not always be the straightest, is the longest continuous carbon chain. Also 1, 2, 3, 4, 5 carbons. Going to also be based off of pentane. The difference here is we have a double bond. So our ANE is now going to become pentene. Now, location of this double bond, we again can number 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5 going right to left. And going right to left does give our double bond carbon number 2, which is the smallest. So basically, we're now going to lock ourselves in to numbering in the left-hand direction. And when we do that, that means that this group here, which is a methyl group, will now get locked into carbon number. And again, it missed it, but it technically should be hanging out at carbon number 3. And putting all that together gives us 3-methyl. Again, a dash between a number and a letter. Dash 2-pentene. Any question on those two there? So again, as we talked about last time, you do want to make sure you kind of check every direction in terms of numbering. Sometimes you'll be surprised that, oh, this one is much longer, and it kind of starts up on top, comes down, goes to the right, goes back up, or something like that. So you do kind of want to kind of quickly, when you're doing these things, sort of check every sort of option in terms of finding that longest carbon chain. And again, the important part here is double bond and triple bond does need to be part of that longest chain. All right, a couple more. Let's see what you do here. To answer your question, when you name something methyl, which is sort of the group that's attached, that's a group which is known as an alkyl group, which is why it's an alkyl group. So it ends in YL, which is why it's already changed to represent that it's not a big chain of carbons. It's actually sort of a group that's attached. So that's why it ends in YL. We only really change the kind of longest continuous carbon chain because that will have a functional group contained in it, and that will tell you what type of organic molecule it is. And anything that is not part of that longest continuous carbon chain is considered some type of group. And those usually, in most cases, will have that YL ending to signify that it is missing at least one hydrogen to allow it to attach to the longest continuous carbon chain. You're welcome. So why don't we take a look and see how we're doing on these? So starting with the top one, that's a lot of carbons. Let's see. We got starting here. We have one, two, going left to right. 1, 2, 3, 4, 5. Then going down, 6, 7 carbons. Going left to right and then going up gives us 1, 2, 3, 4, 5, 6, 7 carbons as well. Starting at the CH3 that's on top, second in on the left, and going down 1, 2, 3, 4, 5, 6, 7, and going the other way 1, 2, 3, 4, 5, 6, 7. So again, it looks really like no matter which way you go, 7 looks like a winner in terms of carbons. So I'm just going to draw a box around at least 7 of them. I'll just go this way. It's a big box. So 7 is based off of heptane. When we look at that longest continuous carbon chain, what we do see is a double bond here. So then we know that our ANE should now become heptene, ENE. And we do want a number. So we want a number whichever way is going to give our carbon, not our carbon, but our double bond the smallest number. If we go left to right, that's 1, 2, 3, 4 carbons until we hit that double bond. If we go right to left, that's 1, 2, and 3 carbons. So going right to left will give us the smaller number in terms of the double bond, which gets the priority here in terms of numbering. So we'll number it this away. And that means that at carbon number 3, we have a double bond. So that's going to then become 3 heptene because of that. We also have a group over here, which is a 1 carbon group. And again, as was a question that was asked, because it's a group, it's based off of methane, but we do change the back part of it to YL, and that signifies that it is not part of the longest continuous carbon chain, but just a group that's attached. On the right-hand side here, we have a 2 carbon group. Again, the 2 carbon group would be based off of ethane, and we drop the last part there, and it becomes a ethyl group. Now, just like what we did on the other one, since we locked into place numbering right to left, we have to keep that designation for everybody. So that means at carbon number 3, there's an ethyl group. At carbon number 6, there's a methyl group. And we do want to put it in alphabetical order, which I happen to have done right there. So putting all that together, that's going to give us 3 ethyl for the one on the right, 6 methyl for the guy on the left on top, and then this would be 3 heptene, ENE, for the double bond located at carbon number 3. If you haven't sort of realized it yet in terms of naming. Really, naming is all about location, location, location. You're really just basically spelling it out for somebody where every single thing is located on that longest continuous carbon chain. It's really just, that's essentially what you're doing when you do this. Any question on that name there? So looking at the bottom one here, if we count, we got 1, 2, 3, 4, 5, 6 carbons. Again, in this case, straight across is your only option. So our 6 carbons is going to be based off of hexane. We have a triple bond in this case, so we're going to drop that, and that's going to give us sort of the base of the name of hexine. We do want a number going right to left. I'll do that right. Right to left is 1, 2, 3 for the triple bond. Going left to right gives us 1, 2, and 3 for the triple bond as well. So again, going in either direction, our triple bond is going to be located at the exact same number. So again, in this case, what you would want to do is default to the next important thing. And the next important thing would be this group attached. This is a halogen, and they are named like bromo. Fluoral if it's a fluorine, chloral is if it's a chlorine. And since we would want to give that group then, because there really is no difference in terms of our triple bond, it's at 3, we would want a number, actually in this case, left to right, where if we go left to right, our bromine group over here is at carbon number 2. So this would be 2 bromo dash 3 hexide. Any questions on where that name came from? Okay. Just see what's on the next page. All right. Let me see here. Let me actually give you a couple of names, and why don't you draw them just to make sure, again, you know how to go sort of both ways, which you do need to be able to do. So why don't you draw, we'll just hope this works. Why don't you draw 2,6-dimethyl 3-heptene. So that's 2,6-dimethyl. We're going to hope for the best there. 3-heptene. And then why don't you draw perhaps, we'll do this one. Again, we'll hope for the best here. Just kind of making it up. Let's go with 1-methyl, 1-propyne. YNE. All right. So take a couple of minutes and draw. You can draw the condensed structure if you like what's on the screen. And make sure, again, you can go the other way, which you obviously need to be able to do as well. Give me 1 sec. Let me just look at your questions, and I'll get you your answers while you guys are working on drawing those. And in terms of your question about the methyl. Is that in regards to the first one? So the reason you wouldn't use 2-methyl is because in this case on the top one, and whenever you're dealing with double bonds or triple bonds, they get the priority in terms of which way you number, and you always want to number the carbons to give them the smallest number. And the consequence of doing that, since we ended up numbering right to left in that top one, when we numbered it right to left and sort of locked it in for our double bond in that case, once you do that, you are stuck with that numbering, which means all the other groups have to be numbered the same way. So you can't have two different sort of ways you're numbering things, because there has to be sort of a consistent way in which you're numbering where everything's at. So basically by us saying 3-heptene, we're saying going right to left is where we're going to find that first double bond. And because that's the way we're numbering all the carbons, we have to keep that numbering for the other groups that are attached. You can't number left to right because, again, the most important thing in terms of the numbering when you're dealing with a double bond and a triple bond is that double bond and triple bond has to have the smallest number. And if you went left to right, that would put your double bond at carbon number 4, which would be a larger number than carbon number 3. So it's all about sort of when you're numbering, what sort of gets the priority in terms of numbering. And in the case when there's a double bond or a triple bond, they always get the priority, and you always want to number whichever way will give them the smaller number. So that's why we had to actually in this case go right to left. Yeah, so in this case of what we're dealing with right now, double bonds, triple bonds, they get the priority regardless of what groups are attached. When we deal with alkanes, it's the groups that are attached because there is no double bond or triple bond. So basically the groups sort of get the priority when you're dealing with alkanes, all single bonds. When we move into double bonds or triple bonds, because those are sort of the functional groups, they get the priority in terms of numbering. And everything is always, you want to do whichever one gets the priority, the lowest number is always the way you want to go. You're welcome. That's okay. That's what we're here for. I'm sure others have the same questions. Not a big deal. And there's a lot of funky rules with organic and naming and what things you do and things you don't do. And truthfully, I sometimes get a little like, oh yeah, there's that weird rule that sort of follows. So it's a lot if you've never done it before, sort of all these kind of weird rules and things that it's okay in this case, this gets the priority. So it just takes a little practice, and you'll get sort of the hang of it. So let's talk about drawing these guys. So remember, when we're drawing things, we do want to work backwards in the name. So we want to kind of start with the back end there. And that back end of the name there, which is heptene, is going to give us a lot of information. The first information is the heptene part of it. Heptene is 7 carbons. So I'm just going to draw it down here since I got a little bit of space. 4, 5, 6, and 7. So we'll squeeze it in. Now, ENE also tells us that it has a double bond. And as we've been doing, we know that the 3 means it is at carbon number 3 where we should find that double bond. As we talked about last time, since you are drawing it, you could number it left to right or go right to left, again, because you're the one drawing it. I'm going to go left to right. So on the very left, I'm going to call that carbon number 1. So I'm going to go carbon 1, 2, and 3. And at carbon number 3, again, that is where I'm going to put my double bond, again, because I went left to right. Just like we were talking about with the naming when we have the picture, because I decided to number left to right, all the other groups has to be numbered that way. So in my numbering scheme, this is always going to be carbon number 1 for everybody going left to right. So that means continuing on here, that took care of that part of it. Dimethyl means that we have not one CH3 group in here, but we do have two CH3 groups. That's what the methyl means. And that is where they're located, carbon number 2 and carbon number 6. So because I went left to right, that's carbon 1. My carbon number 2 is going to be here, and I'm going to draw it up on top. Again, you could draw it on the bottom. It's fine. That's number 2. That's number 3. That's number 4. That's number 5. And that is number 6. And just to mix it up, I will perhaps just draw it down here so it doesn't get too mixed up with that blue. You could draw it on top as well. At that point, that takes care of everybody there. So if you remember, when we're done putting all the groups and everything attached, everything else is going to be hydrogens. And everything else will be hydrogens until each of the carbons end up with only 4 bonds. So you could do it by counting how many lines are coming into the carbon. This carbon has 1 line coming in, which means it needs 3 hydrogens. The carbon next to it on the going from right to left has 3 lines coming in, which means it actually only needs 1 hydrogen squeezed in there. The guy next to that one has 2 lines coming in, which means he needs 2 hydrogens. The guy next to him has 3 lines coming in, which means he only needs 1 more to get the 4. The guy next to him has 3 lines coming in as well. We'll need 1 more to get the 4. The guy coming next to him also has 3 lines. He will need 1 more. And lastly, the guy at the end has only 1 line coming in. He will need 3. So just to kind of make it a little prettier. Any questions on that one there? And CH3. Okay. So looking at our next one, which is right here. Again, we're going to take the same approach. We're going to work backwards. So starting right to left here, the propyne tells us a couple of things. Propyne is based off of propane, which is 3 carbons. So that's a good place to start. I'm just going to do on the bottom here. Draw some 3 carbons. Going to be trade space this time, maybe. And the YNE tells us it is a triple bond. And the 1 tells us it is at carbon number 1. So remember, the name really does give you a lot of information. Same deal. I'm going to go left to right. You could go right to left if you chose. So at carbon number 1, I should put a triple bond happening. That takes care of the back part of the name. And also at carbon number 1, we have a methyl group. So since I went this way as carbon 1, we would put a CH3 group over there. And everything else should be hydrogen. So he has 1 line, which means he needs 3 hydrogens. This carbon actually has 1, 2, 3, and 4. He doesn't get any hydrogens. And this carbon here actually has 1, 2, 3, 4. He doesn't need any hydrogens as well. And there it is. Yes, so that would be 1 methyl, 1 propyne. So again, as we talked about last time, sort of drawing it from the name, it's, I think, the easier move. Again, you just want to always work your way backwards. You will also notice that sometimes when you draw these guys, when they give you a name, and then you look at it, you would probably call this, if you were just given the structure, 1, 2, 3, 4 carbons. And that would be something like 2-butyne. So sometimes that happens. Sometimes you'll have a name like we had up there, and then when you draw it, you're like, if I count out all those carbons, it's actually something else. And it does happen that way sometimes when you sort of have a name. sometimes people make up names and stuff like that, and sometimes it actually can be named correctly a different way once you actually draw the picture. But that would be the correct sort of drawing for that name. Question on how to draw these guys. Obviously, you need to be able to go both ways, name and draw it. Okay. Now, if we got some of these guys with our halogens in there, again, the way that we name our halogens are chloral for chlorine, bromo for bromine, fluoral if you had a fluorine, iodo if you had an iodine, so IODO for that guy. Same deal here. For example, we can see we got 4 carbons. This is our longest carbon chain. So 4 carbons with a double bond would be butene. Going left to right gives us 1, 2. Going right to left gives us 1, 2. So it is going to be 2-butene no matter which way you go. But again, now we would default for this guy and want a number this way, because it doesn't matter for the double bond in this case, but it does matter for the chlorine, and that would give us the 2-chloral 2-butene. Same thing here, 1, 2, 3, 4, 5, 6 carbons. 6 carbons based off of hexane. Has a triple bond, becomes hexine. Going left to right gives us 1, 2, and 3 for a triple bond. Going right to left gives us 1, 2, and 3 for our triple bond. Again, for our triple bond, it is a tie no matter which way you go. So again, we want to then default to our bromine, and we would want to go left to right in this case, as it would give us the smaller number, and that would give us 2-bromo 3-hexine. Coming this way, we got 1, 2, 3, 4, 5, 6, 7, 8. 8 off of octane. Because there's a double bond, it becomes octene, E-N-E. We got 1, 2, 3 going left to right. 1, 2, 3, 4, 5 going right to left. So left to right is where we want to go. Again, the double bond would get the priority here. And this would be 3-octene. Since we have to go this way for our double bond, that means our groups are going to be named or numbered off of this. And that means at carbon number 2, we have a methyl group. At carbon number 6, we have a methyl group. And again, that is 2 methyl groups in the same compound. That is how we get to dimethyl. So putting all that together, at carbon number 2, comma, carbon number 6, there is dimethyl 3-octene. Putting all that together. And lastly here, just to kind of go through these, we got 1, 2, 3, 4, 5, 6 carbons. We have 1, 2, 3, 4, 5 carbons if we went down. So 6 carbons, again, based off of hexane, going to become hexene with our double bond that's located there. And our double bond is at carbon number 3, no matter which way you go. Now we have a couple of options here because we actually have 2 groups attached. We have a chloral group and we have a methyl group. And if we go left to right, it is 1, 2, 3, 4, 5, 6. We go right to left, 1, 2, 3, 4, 5, and 6. In terms of the groups, they are both located at carbon 3 and carbon 4, no matter which way you go. So the question is, which way should you go? And remember that when we put the groups together, it is alphabetical. So this is a methyl group. This is a chloral group, which means alphabetical wise, chloral should come before methyl. which means we actually would want to give the chloral group the smaller number. So we would actually want to go in this case in this direction, because we sort of defaulted all the way to the end. And at the end, the last sort of important thing after we got past the double bond and everything else is alphabetical in terms of the groups attached, and the chlorine is alphabetically before the methyl group. So that, putting it together, would get us 3 chloral, 4 methyl. I'm going to run out of room, so I'm just going to dash it here, and we'll come this way, yeah? So I'll just do the arrow. We'll just pretend that's a big dash. So it is 3 chloral, 4 methyl, 3 hexene. Again, not that big of a dash normally, but we'll just make a U-turn there. Any questions on sort of those names? So what this hopefully should demonstrate is sometimes, like you've been seeing, no matter which way you go, left to right or right to left, you are going to run into almost like a tie in terms of, say, double bond or triple bond. So then you want to think about the next important thing, and that usually will be the groups attached. And if there's just one group, then you want to go whichever way gives that one group the smaller number. But in like this last example, if there are 2 different groups attached, you want to go whichever way gives the one that is alphabetically should come first, the smaller number. Any questions on any of that stuff there? So let's talk about isomers, and specifically isomers that involve double bonds. And as you might remember, like we talked about with alkanes, and sort of the reason why a lot of times when you have alkanes, I think there was a question like, can I draw the group up or can I draw the group below? And you really can with alkanes, because when you have a carbon-carbon single bond, it is free to basically rotate around in a circle. So if you kind of like think of the bond and just go around, you hold your finger out straight and take your other finger and go around it. That is sort of how free the bond is to rotate. And we actually start to lose that rotation or the ability of those things to rotate when we have a double bond involved. So when we have a double bond involved, it kind of locks everybody into place in terms of their 3-dimensional arrangement. And what that means is they no longer can rotate. And what you'll end up getting is you'll end up getting groups that are trapped either on the same side of the double bond or on opposite sides of the double bond. And remember, isomers are really the same molecular formula, but a different connection of how they are put together. And when we get into double bonds and isomers, we get what are known as cis or trans isomers. And cis means that the groups attached are on the same side of the double bond. So they are on the same side of the double bond. And the double bond is the most important thing when you're trying to identify cis or trans isomers. Trans is pretty much the opposite, and that's basically what it means as well. It means that those groups attached to the double bond are on opposite sides of the double bond. So when we look at these 2 guys here, when we're doing cis and trans isomers and we think about groups like methyl groups, so we have a methyl group here and we have a methyl group here. They are the same group on different carbons, and they are on the same side of the double bond, which means this would be our cis isomer. When we look at this guy, the CH3 is on top, this CH3 is on the bottom of the double bond, and they're on opposite sides of the double bond. and this would be our trans isomer. Now, when you're doing cis and trans, although we don't a lot of times think of hydrogen as being a group, you can sort of think of hydrogen as a group. And we even see with the hydrogen, this hydrogen and this hydrogen are on the same side of the double bond, while this hydrogen and this hydrogen are on opposite sides of the double bond. So there are some rules in order for you to basically have a cis or trans isomer. In order to have a cis or trans isomer, when you look at the double bond, which is the most important thing, first off, on each of the double bonds, you need to have two groups attached. And again, that group could be a hydrogen that are different. So on the same carbon, they need to have two different groups. And the second thing that you need in order for that to occur is on opposite carbons in the double bond, you need to have a group that is the same. So for example, if I had A here and say this is C. Actually, we'll use D, so C is not a good idea in this case. We'll use D. Very badly drawn D. So that is essentially what you need to have in order for an actual cis or trans isomer to exist. You need to have a double bond. And in that double bond, you need to focus in on the carbon-carbon double bond. And within that carbon-carbon double bond, the first thing that needs to happen is on both of those carbons, they need to contain two different groups. Then they also need to contain a group that is the same on each of those carbons. And you would look at the groups that are the same on each of those carbons, and you would decide, are they on the same side of the double bond? Or are they on the different side of the double bond? So these are sometimes given in names as well. So this is 2-butene, and this would be cis 2-butene, and this would be trans 2-butene. So you may say to yourself, how did we get to butene? When it is drawn like this, sometimes people only focus in on your double bond. But if you do the longest continuous chain, there's a carbon there. That's 1, that's 2, that's 3, and that is 4, which is how we get to our butene. So sometimes when people see it drawn like this, they will just think about the 2 together, but your longest continuous carbon chain actually is still 4 in a row, which gives you butene. So let's take a look at some examples here, I think. There you go. So hopefully that's exactly what we were just talking about. Guess I shouldn't scribble all over the page. Why not? All right, so our cis and trans, as we can see here, these are our skeletal structure, not really skeletal structure. These are our model structure. And again, that's our CH3 group on each of them. They are both on the same side of the double bond, as you can see. And again, that's going to give us the cis, while this is our CH3 here and our CH3 here, which again is on opposite sides, which gives us our trans. So again, this is maybe a better diagram of what I was just trying to explain, but those are the two things that you need to look for to know if it can exist. So there is a case where you will get perhaps a double bond and you cannot have a cis or trans isomer. So what we see on the screen here is what I was just talking about. This is what you need to look for to make sure that a cis or trans isomer could exist. First off, when you look at the carbon-carbon double bond, which is the most important thing here, each carbon in that carbon-carbon double bond needs to have two different groups attached to it. And then again, on the two carbons, you need to have a group that's the same on both of these carbons. So those are the two things that you want to look for. If you don't have that, then you will not have a cis or trans isomer that is possible. So that is what we're talking about in this example here. Although somebody drew it kind of like it had sort of a cis or translocation. When we look at this, first off, we want to focus in on the double bond. We want to look at the groups attached to the double bond. So we have a hydrogen here. We have an ethyl group here. Those are different, which is good. But when we come to the other carbon, that's a hydrogen, that's the hydrogen, that is the same group attached, which means that is bad. So that means you cannot have a cis or trans isomer in this case, because essentially when you sort of move it around, it's really the same molecule. This is what this is trying to show you, that even though you may draw it differently, it will end up being basically the same molecule in three-dimensional space. So not everything that has a double bond can do cis or trans isomers. Those two things about having the same different groups on the same carbon and a group that's the same on two different carbons is really important in identifying them. So isomers could be stereoisomers, and these are isomers that only differ in the arrangement or 3D arrangement of their atoms. So if we look here, again, this is the one we were looking at. That's our two groups that are the same. And again, this is different and this is different. This is different and this is different. So again, we can't have that cis isomer. While over here, again, like we saw earlier, our groups are on opposite ends there, which would be our trans. So constitutional isomers are essentially the same. Stereoisomers are guys that have different three-dimensional arrangement, and constitutional isomers have sort of a different connection that occurs. So they have different ways that the atoms are bonded to each other. Again, in this case, the difference is here we have a run of CH2, CH3, while over here we don't have that run. We have this sort of run of carbons together. So that's why these two guys are constitutional isomers, different bonds, and stereoisomers are different arrangement in three-dimensional space. So let's take a look at each of these, and why don't you take a moment, and why don't you take a minute and decide, is A, B, and C, the pictures that are down there, are they a cis isomer? Are they a trans isomer? Are they neither? So take a minute or two and see if you could correctly identify these guys as either cis, trans, or again, neither. Okay, so let's take a look here and see how we're doing. So again, when you look at these guys, it is always the carbon-carbon double bond carbons here that are the important ones. So the first thing you want to make sure is, does each of those carbons have different groups attached? So I'm going to kind of circle them. So on the carbon on the left, we have a methyl group attached, and we have a hydrogen that's attached. So these two groups here are different from each other, and that's good so far for it to be either a cis or trans. When we look at the other carbon, this entire thing here is a group, it's isopropyl. And this guy over here is a group. And these two guys are also different. So that's a check and a check so far in terms of could it be cis or trans. The second important thing is now when you look at each of the carbons that are there, is there a group that is the same on opposite carbons? So hopefully you should be able to recognize that on the one on the left, we have a CH3 group. And the one on the right, we have a CH3 group. So that also allows us to meet the minimum qualifications for a cis or trans isomer to occur. So this is a cis or trans. So now we want to determine, is it cis or is it trans? And it is the double bond here we're looking at. Now the groups that's the same on opposite carbons are on opposite sides of the double bond, which means this guy here would be a trans isomer. Any questions on how we went through that there? Now, if we come to our next one, again, we're going to focus in on the carbon-carbon double bond. So if we look at the one on the left, we have a Cl attached and we have a CH3 attached. So these guys are different. So that's good so far. Now, when we go to the other carbon, we have this big group attached, kind of an isopropyl group. And we also have this group attached, which also looks much like an isopropyl group. These two guys are the same. And as soon as you hit the same, that is done. This has neither in this case. So this is neither because of that. You cannot have the same group on the same carbon and have a cis or trans isomer occur. Again, you'll end up with the same molecule if you move it around. You won't end up with anything different. And lastly, when we look at the guy in C, we have a double bond carbon. Top guy here, 2 carbon group, like an ethyl group. Bottom guy is a hydrogen. Those are different, which is good. Right-hand side, we have an ethyl group and we have a hydrogen. Also, those both are different. And now what we're looking for is a group that is the same on opposite carbons. And in this particular case, you have a couple of options, but we have our ethyl group and we have our ethyl group, which are the same on opposite carbons. And that means that since they are actually on the same side of the double bond, this would be a cis isomer. So first one's a trans, second one is neither, and last one there is a cis isomer. Question on any of those there? Now, before we wrap it up for tonight, if we take a look at this first one, let's kind of redraw it real quick. Why don't you take a moment And why don't you give the correct name for that? So take a second here, a minute or so, and see if you come up with the correct name for that, which was what was in part A there. All right, so let's take a look. So remember, although it is sort of drawn in the trans sort of formation, we still want to look for the longest continuous carbon chain. Since it does have a double bond, it does need to include that. So if we go 1, 2, 3, 4, and 5, you can also go 1, 2, 3, 4, and go this way for 5. And you can go backwards as well. So 5 does look like I'm not sure. There's no black box on mine, I don't think. So there's 5, so we can get it either way. We'll go this way. I think everybody can see. Yes, I hope. So that is 5 carbons, which is based off of pentane. It has a double bond, so it is going to be pentene. And pentene, we do need to give the double bond the smallest number. We have a methyl group hanging off over here and a methyl group hanging off over here. And we are going to give it 1 and 2. If we go the other way, 1, 2, 3. So this is going to be 2 pentene. And since I numbered 1, 2, 3, 4, and 5, that means that carbon number 3 and carbon number 4, there are 2 methyl groups. So this would actually be called 3,4 dimethyl 2 pentene. And because we identify this as trans, sometimes people will put the trans in front of it. So this would be trans 3,4 dimethyl 2 pentene. The purpose of that is just to remind you that even though sometimes things are drawn a little bit different, you do want to make sure you still look for the longest continuous carbon chain. Again, very commonly, especially when they're drawn with the cis and trans, people just kind of go, oh, there's only 2, and because they're so focused in on sort of the double bond part of it. Any questions on cis or trans isomers or naming or any of that type of stuff? Okay, so I guess we'll stop there today. We'll take maybe a 10-15 minute break, and I'll open up discussion if you do have any questions or anything like that. Other than that, I think that should do it for today in terms of lecture. I'll see you in a bit if you're coming to discussion. If not, have a nice weekend, and we'll see you on Monday. If you're not going to show up to today's discussion, I guess we'll see you in Monday's discussion. All right, have a good one. Again, discussion will start in about 15 minutes.